Good afternoon everyone. I hope you can hear my voice. So we will start the week 5 tutorial class today. So first we will go through the lecture words are followed in last week. So here in the lecture first we started with the history of quantum mechanics, right? So from if you say about the history of quantum mechanics, first we have to discuss about the black body radiation. Then discrete nature of atomic and molecules, then Compton effect, photoelectric effect. Why we have to discuss about this four property? Because these four properties can't be explained by the classical physics, so that's what people started to understand more in the more atomic level or molecular level, the quantum mechanics which is originated. So first, what about the black body radiation? So an electromagnetic radiation which coming off from a body, that black body radiation which is like a thermal equilibrium condition, for example graphite surface. So Kirchhoff, which designed a black body in 1859, known property for the black body radiation. So first property is what? As temperature T of the black body increases, means body increases, intensity of the radiation from the body also which increases. Similarly, higher the temperature, lower is the wavelength of the most of the intense part of the spectrum. So in black body radiation, what are the things? Energy, that we can tell it in the joule, energy per unit area. Joules per meter square, power per unit area. That is joules per meter square second. Okay, then spectral radiation. Radiance, that will be Weber per meter cube. Okay, so now we know the plot graphical representation of the black body radiation. So how it will be? Right, so here the wavelength which we can measure in the meter, and here the spectral radiance, that is Weber per meter cube. Okay, so intensity of the black body radiation, how we can represent it is temperature dependent, integral 0 to infinity r of lambda d lambda. So for this is first T1 temperature, this is corresponding to T2 temperature, so T1 which is greater than T2. Okay, so intensity, how we can measure the area under the curve itself. Then one more law we have to remember, that is Stephen Boltzmann law, that I of t is equal to sigma t to the power 4, where sigma is equal to 5.67 into 10 to the power minus 8 Weber per meter square Kelvin power 4. Similarly, we have to remember Wien's displacement law also, that is equal, what is Wien's displacement law? Lambda maximum into temperature, that will be constant. Okay, what is a spectral radiance? That spectral radiance you can denote it by the R of lambda comma t. It is dependent also length and the temperature is defined as the R of lambda d. Lambda is the power per unit area whose wavelength lies between the lambda and lambda plus d lambda. So intensity that we can measure by integral R of lambda d lambda, that will be sigma t to the power 4. Okay, so what is R of lambda and t? That is Rayleigh-Jeans law say that R of lambda t is equal to 8 pi kt divided by lambda power 4. Okay, this we have to remember for our understanding. From that, so what is the Planck's explanation for the that is R of lambda comma t, that is equal to 8 by ch divided by lambda power 5 into 1 over e to the power hc by lambda kt minus 1. So higher lambda values we can make an approximation that e power h lambda hc by lambda kt minus 1 nearly equal to hc by lambda kt. Okay, then R of lambda kt become 8 by ch divided by lambda power 5 into hc by lambda kt. Okay, so an arbitrary input, that is condensed energy of this oscillations, and h nu is the quantum of light. Now we will discuss about the photoelectric effect. So the main key features are what? No electrons are ejected regardless of the intensity of the incident radiation unless that frequency nu exceeds a threshold value. Then second point is the kinetic energy of the ejected electron increases with the frequency of the incident radiation and is independent of the intensity of the radiation. And the third point is even at the low intensities electrons are ejected if the threshold is exceeded. So we know that the formula like half m v square is equal to h nu minus 5. Okay, so the explanation of photoelectric which suggests what the EM radiation of the frequency nu cannot have any arbitrary energy, that can only possess the energy of a quantum value, that is h nu in 2h nu, 3h nu and nh nu values. Okay, then EM radiations of the frequency nu behaves as the so it is consist of 1 to n particle each with energy h. There is a particle of light came to be known as for the photons, and Newton also thought the light is a corpuscle, but his idea was abandoned with the discovery of the interference and the diffraction. So light has dual nature. It is like a wave nature as well as the particle nature. So light can be divided as a particle. Science, so Planck's etc. They were doubtful about the quantum nature, although no photoelectric effect. 1921 Albert Einstein did. Like Louis de Broglie, at any particle traveling with a linear momentum p can be at the thought of having the wavelength lambda, so that like lambda is equal to h by p. So dual nature, which is explaining here the wave particle duality from the de Broglie's idea. So particles could have thought of the wave successfully explored by the Davis and German experiment. So they demonstrated that beam of electron could diffract. Similarly, the electron from a heated filament incident on a nickel sample demonstrated as a diffraction in 1927. Now, how we will interpret the quantum mechanics part? So we know that wave function psi obtained by solving the Schrodinger equation, that is minus h cross square by 2m del square psi plus v of del square plus v of psi is equal to a psi. Okay, so this is the Schrodinger equation, so it cannot be solved by for the first principle. So Einstein, Erwin Schrodinger, Paul A.M. Dirac, they got Nobel Prize for this in 1933 for new productive form of the atomic theory. From here we can tell about the probability of finding particle between the x to x plus dx distance, that is the psi star dx or mod psi square dx. Okay. So the wave function psi can be considered as a sum of the mode of the one of the wave functions such each having a momentum value. In such cases, same measurement will be indicate one of the value of the momentum and the other measurement result to the value of the other momentum values. Okay, so localizing a particle will require that the probability of finding particle in a very small region, it should be nearly 1. So let's wave function should be look like delta p delta x greater than or equal to h by 4 pi. So this is the theoretical reality in Heisenberg's uncertainty principle that we know already. So in summary, we can say that h is equal to h nu. This is given by the Planck's. Okay, so lambda is equal to h by p. This is de Broglie, and minus h crew squared by 2m del square plus v of psi, that is equal to a psi. This is Schrodinger. Okay, then psi square dx, that is Bono. Then similarly del x del p greater than or equal to h by 4 pi, it is Heisenberg. So now we'll go to the introduction of the Sommerfeld model. So we know that in Heisenberg 1932 Nobel Prize is in physics, Debye in 1930 Nobel Prize in chemistry, and Paul in 1945 Pauli exclusion principle and Nobel Prize in physics he got, and Hans Bethe 1967 generation of the energy in stars Nobel Prize in physics. Okay, so his student is the Arnold Sommerfeld, that is Drude Sommerfeld model, and what he say a free electron model, that is, and applies quantum mechanical principle to the Drude model, applies the Pauli exclusion principle, and potential is constant within the metal. So the implications of the Drude Sommerfeld model is electrons are identical and indistinguishable, and Fermi-Dirac static Pauli exclusion principle, the particles are identical and indistinguishable, and is they discuss about the half integer spin particles. Drude's model, what is happening, which is dealing with the classical particles, and Maxwell-Boltzmann statistics are obeying, and Drude's Sommerfeld model, electrons are which are the fermions, which is obey the Fermi-Dirac statistics. So the difference between the Drude's model and Drude Sommerfeld models are like classical statistics, the swapping the particle between the energy level to new state, but in Fermi-Dirac particle, the swapping the particle between the energy state do not give a new state, it's sum of the its same old states. So the manner of counting the number of microstates which is different here, and there is a fixed number of state at each energy level, that's like Pauli exclusion principle. Okay. So please just go through the theory part, whatever we have discussed, then we will start the problem solving session for the last week. Even try to answer these 4 questions, then we will go to the next one.
Ma'am, what's the answer for the first question?
Yeah, Kirchhoff laws with respect to the about. So first we discussed today itself, right? What will be the answer for that? Where the Kirchhoff law discussed black body radiation. What about the answer for second one? Human body emits what kind of radiation? Is there any guess?
Infrared?
Yes, infrared. And the third one, the Compton theory is based on the collision between an electron and a
Photon.
yes. Now fourth one, classical physics failed to explain because the quantum mechanics nature of the particles. Which one is
All of the above?
all of the above? Correct. Now see the match the following. First match the equations, then we will discuss it.
Ma'am, first one is 1D, right?
Mm.
Then 2C,
1D
2C,
plus
then 3A,
3A 4B.
4B.
What about this?
Planck's constant C,
Planck's constant C.
speed of light A,
Mm.
uh, Boltzmann constant B,
Mm.
then Stephen Boltzmann constant D.
Yes, correct. No, this one.
Ma'am, ma'am, Max Planck quantization of energy,
Mm.
de Broglie wave particle duality,
Mm.
Schrodinger wave equation,
What? Schrodinger?
wave equation,
Mm.
Heisenberg uncertainty principle,
Mm.
Max Born interpretation for wave function, Einstein light can be treated as particle.
Correct. Now try to answer these three questions.
The first one is both use the concept of free electron model and both models assume that potential is constant within the solid.
Yeah, so both answers are correct. Both use the concept of the free electron model, and both models assume that the potential is constant within the solid. So what about the fermions are the particles which are
Identical and indistinguishable and has half integer spin.
identical and indistinguishable when half integer spin? Yes. Now next question. Dude Sommerfeld model and Wood models are follows.
Maxwell-Boltzmann statistics and
Actually,
Fermi-Dirac statistics.
read the question carefully. Which one is first?
Fermi, Fermi-Dirac statistics and
Fermi-Dirac
Maxwell-Boltzmann.
statistics and
Maxwell-Boltzmann statistics.
yes. Now try to solve the first question. A sample absorb radiation 530 nanometer and re-radiate energy at 633 nanometer. What is the frequency of oscillation amid the radiation? So which formula we have to use?
E minus E0 is equals to h mu.
What are the parameters given?
The initial energy final energy is given.
Hmm.
So subtract them and divided by h.
Okay, then try to do. Then let me know the answer.
Ma'am, I'm not getting the answer for that
Yeah,
question.
actually you have to use the formula because it's asking the emitted energy, right? So you have to use the formula nu is equal to c by lambda. Okay, so see, you know already the value lambda, you can use 633 nanometer converted into meter, then solve, you will get the answer.
Ma'am, option B.
Yeah, 0.47, that's the correct answer. Now second question, the black body radiation plots in between the spectral radiance and the wavelength of the emitted radiation at the temperature T. If the temperature of the black body radiation decreased by 20 degrees Celsius, then the area under the power density per unit wavelength versus wavelength curve will be.
Decreases.
Increases, yeah, it is decreases. Okay, so what is mean by this area under the power density per unit length versus wavelength? It is nothing but intensity, right? So intensity formula is sigma t to the power 4, so it will decrease. Okay, now what about the third question? The two samples A and B at the temperature 25 degrees Celsius and 100 degrees respectively kept in a dark room. Calculate the peak radiation wavelength for the sample A and sample B. How to find it? Lambda max T is equal to 2898 K micrometer K. Okay, so from here you can find the lambda max value. So find for those two and tell me the answer.
I couldn't understand that formula. Can you
This
explain it?
this formula is the lambda max T is equal to 2818 micrometer Kelvin. That is the formula for the calculating the wavelength peak for a black body radiation. Okay, and what here asked, the peak where radiation wavelength is asked in the question, so corresponding temperatures. So that temperature you have to convert it into Kelvin, then substitute here, then you will get the answer.
Ma'am, option A.
9 and 7. That is the correct answer. What about fourth question? Proton and electron differ from each other because of
Charge and mass.
and size also. Now calculate the approximate intensity of a black body heated at 4727 degrees Celsius. Okay, so how to find it? Convert into Kelvin and do the calculation.
Ma'am, option D.
B or D?
D.
Yes.
Ma'am, first and fourth.
Hmm?
First one is false.
first one is false. The diffraction phenomenon was originally interpreted as the experimental confirmation for the particle-like behavior of matter, that is false. And second one that we have done already. The third one, Rayleigh's law is
not applicable at lower wavelengths. Ma'am, the fourth one we did, right?
Fourth one we did.
Is equivalent to a black body and will display net absorption of energy.
Yeah, these two answers. A graphite dye heated at 1200 degrees Celsius for 30 minutes and then immediately kept in a location that's at room temperature, then it is equivalent to a black body and will displace the absorption of energy. And this one we have done.
Indistinguishable nature of electrons and need to use Fermi-Dirac statistics.
Then the next one, protons that we have done, the master size. This one, calculate proton intensity of a black body radiation for 77 degrees Celsius.
As we did, ma'am.
Yeah. Now just go through the few problems which are related to the fourth week classes. Okay.
Ma'am, I got this question.
Yeah.
I understood.
And this one is also like temperature dependent to temperature while is given depends the ratio of the most probable speed of the particles, like similar kind of problems.
Ma'am, can you show the next question?
Yeah. Hope you have done all the problems. Okay, so today we'll stop here, then we'll continue next class.
Thank you, ma'am.